I don't know, JD, are you there?
Hello, good
Let's
evening.
get started. Are you there? I think so.
Yes, Reggie, I am here.
Is it Jyotirmay?
Yes, it's me. Hello,
Sure.
Reggie.
I guess so though. Can't hear you. You're there, right? Wait. I have to. Can you speak again once?
Hello.
Yeah, I can hear you. It's Jyotirmay, right?
Yes. Good evening.
Good evening. Good evening. Hi. Sorry, I couldn't hear. I had muted my system.
Okay,
Anyways,
no issue.
any questions or anything do you have?
No, I mean, up till now, no.
Okay. How any feedback on how are the video lectures now that you have done half of the course? Any comments?
So far, okay. Means as per NPTEL.
Okay. Is it good? Is it? Are there any areas to improve? Something that remains unclear? It's just that some interaction with the students makes it better for both the instructor and the students. I can discuss things which are more which a student or majority of the students will be interested in, and also I also have a direction where to take these sessions. But anyways, so I'm recording. My audio is fine. Yeah, you're good to go. If you are aware, what was the video lecture for this week was about? If you could slightly talk about it briefly.
It was more on the second law of thermodynamics. That is the basic concepts.
But I think entropy as a property has not been introduced yet, is it?
No, it will be coming in the next week. In that we will have second law of thermodynamics and then the applications of second law of thermodynamics in entropy.
Got it. Okay. Okay. So largely theoretical, right?
Yes.
even numerical anymore, analytical anymore, right? Anyways, so if I go through the questions, I might quickly finish. I don't know if something else, if we discuss something else, or I just continue with this. Just give me a second. Just give me a second. So, let's start the questions and answers, and then we'll towards the end. Let's see if you have some time. Then we'll see what to do. But it's, so the first question is here. What is it? What is the first question? So take the correct statement about first law and second law of thermodynamics from the given options below. Uh, so the options are of this sort. E is this, B is this, C is this, and D is this. If, sorry to bother you, but would you like to take answer this question? With the correct statement of
It
yeah.
can be, I mean, it can be C or D, seems.
Okay. And would you like to tell me why?
This is constant. And yes.
C or D? You couldn't guess it between C and D, which one would be correct?
Actually, I think it seems to be D because conservation of energy. This is basically Q, the amount of energy that you give in a system, it should be able to in the form of internal energy rise plus W, work done in case of a movable boundary. So the D seems to be more conservation of energy in a process.
Right, right. Simple question, nothing much. You are right. This is the correct way. Let me highlight it
But
with a
both
green
almost
color.
similar.
Okay. This is a good point. Why C is different from D? Can we not make it like similar to D? What makes it not similar to D?
Yes, yes, that I was wondering.
You understood why? Can you tell all like for the benefit of people who are watching it recorded? Can you tell why this is not similar to the like C and D are different? Let me break this down. Uh, does C say this or not? Tell me this. E total is equals to E naught is a constant. Is that what C says? Do you agree with that?
Yes, total energy is constant.
But what does D say? Can you tell me what does D say? Like I'm just asking what is the conservation of energy in a process? The general statement of conservation of energy that's what I'm trying to just uh, get it from you. What is the general statement of conservation of energy for a process? Like the most general one. No? Okay. So I'm pretty sure you will be able to say this at least. So first of all, this first one says that this is zero, or equivalently, let me write this, or equivalently, this is dE total by dt is zero. That is what it says. Okay. C point. So like this is this. But now in this one, we basically apply the conservation of energy, which is some, maybe I've written it somewhere earlier. Let me copy that. Hmm, where I must have written this. Yeah, no, it's not there. Yeah, this one, this equation, right? This is what I was trying to answer. Ask. Uh, and we just said TE total here. Isn't it? This is the most general form. We have taken care of unsteady processes. We have taken care of control volume, control mass kind of thing. This is valid for a control volume also. And whatever is valid for a control volume also, it should also be valid for a control mass, right? Because control volume is a subset of control mass. Control mass is a subset of control volume. Do you agree or disagree with that?
Yes, agree.
Yeah, for a control volume where there is no mass exchange becomes a control mass. So control volume or I guess, yeah, control volumes are more general in that sense. Okay. Okay, fine. Let's move to the second question. So just this makes it different. So we are not saying that this will always be zero. This will always be zero, can you tell me that? This is also valid. When will this be zero? Or when do we apply this thing to be equal to zero? What condition is that?
For a steady state process, maybe
Yes.
dt by.
The first true only for steady state. Right. Okay. Let me mark this as important. Then comes the second question. Let's get on with that. Again, can I ask you to answer this, or would you like to try to answer this? What is Hess law? I don't Hess law, man. Read about this. Okay, fine. Let's see. Did sir teach you about Hess law in his video lecture?
Yes, law. Well, I don't know. I mean, I have to check. This Hess law, I don't know.
Yeah. Yeah, I don't know. So let's see. Okay. Maybe you can look for Hess law as such if you want to. You can together see what Hess law is about. If it's not here, not his.
I think this is concerning some total enthalpy change for chemical reaction.
Hmm. Where would I find it in a textbook? It's in the textbook. No. Wait. There. Huh? Yes. No. It's not in this book to start with. Okay, let me try this. The good book too. What is the pretext of Hex law? Let me see the video lectures. See if sir talks about this.
This concerns chemical reaction, I think.
Yeah, but it is there in the assignment set for this week. So, anyways, this is a good opportunity to. Do you want to do it towards the later part of it? This Hess law question. When we are done with all other questions, then we can look at it. Okay, we'll come back to this question then.
Okay.
Is that is it there? Okay. Then let's look at the third question. Because you have skipped second. Okay. Again, same thing. This is a multi-choice thing. Which statement correctly describes the working principle of a refrigerator? Oh, there are too many. No, there are only four options. A refrigerator transfers heat from a low temperature medium to a higher temperature medium without requiring work. A refrigerator transfers heat from a lower temperature medium to a higher temperature with the help of external work. A refrigerator violates the second law of thermodynamics. A refrigerator operates as a heat engine. As a heat engine. Okay. Pretty straightforward, right? These questions are just pretty,
I think it's B, should be B.
yeah, pretty straightforward. Don't know what to discuss in this. Okay. So if this were true, it would violate second law. And how can I correct this one? Can I correct this one? I can though, right? I can correct this one. Can I correct this statement? If I have to change one, like, how do I correct this statement?
From if I go to statement 1, then it should be heat from a higher temperature to a low temperature while giving out work.
So you're telling me about the this one, right? A.
Yes, in this term, yes.
Yeah, so this should be with requiring external work. So this is fine. And which makes it B. C is that it does not violate the second law. But what about this one? Option D. Can we correct this one? Do you know what a heat engine is? Pretty sure you would. Just for the sake of essentially, go ahead, go ahead.
So it will basically be converting this energy into mechanical work through a
Right.
cyclic process, or we can say that it should take the Q from the higher value, and it will means leave out the Q at the lower temperature.
Understood. Yeah, you are
Yeah.
on the right. Like whatever you're saying is correct and accurate. One, I think this could have been corrected, though. Like I, in my mind, I could just correct it like this. Comments, questions? Comments, questions, anything? What is a heat pump? What did I just do? Anything?
It's just a heat pump.
Okay. What is a heat pump? Did you ask?
Heat pump.
Okay, so I'll just introduce this for everyone. So essentially, in the second this chapter, whatever you've discussed, there are three concepts. If you realize, there are three concepts that you are introduced with, and then for the rest of the course, you're expected to know these definitions. Okay, so there is one refrigerator, which is very weird because refrigerator is an appliance. Why are we bringing it in a context of thermodynamics? Well, the reason is that it works on a thermodynamic principle, thermodynamic cycle. So that's there. Then comes a heat engine. Now, heat engine is generally a category. It is not a appliance or anything. But anyways, the third concept is heat pump. Okay, and I am pretty sure this must have been discussed with you uh, in the lectures, but just not that's like in a proper context. So what I'm trying to say here is in the sixth chapter, implicitly you are introduced with these three concepts without realizing, right? There are two statements of second law. One is what is the first statement? Don't remember the first. One is Clausius statement. No, one is Kelvin's statement. The other one is Clausius statement, I think. Let me check. Um, there are two statements of second law, right? And implicitly, you are expected to know what a refrigerator is and what a heat engine is, right? That is what I was trying to say. There is another component, like another thermodynamic device that you are expected to know, which is a heat pump. There are two statements. What are those two ones? Calvin Planck and Clausius. Yeah. So one is Calvin Planck, and Calvin Planck is associated with heat engine. Is that okay? Then refrigerator is about Clausius. Is that also okay? And I think uh, heat pump also comes in here. So let's go by this one properly. Let me explore, like let me go through the second law chapter. So they talk about thermal energy reservoirs, and then the first thing is heat engines. They actually introduce you to the concept of heat engines, thermal efficiency, and then comes the Calvin Planck statement, which is what it is about heat engines. So it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Now, if you look at it, it is kind of saying it is impossible for a heat engine to not reject heat, right? Because a heat engine is expected to absorb some heat and then produce work out of it. So this is like a heat engine statement for second law. And then comes refrigerators and heat pumps. Okay. Uh, then they discuss COP, coefficient of performance. And where comes the second law? It is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a lower temperature body to a higher temperature body. Okay. So in a sense, Clausius statement is indeed universal to both of these. And I'll tell you why. See, refrigerator is defined as a device which absorbs heat from your system and rejects it to the environment. Okay. Now, if the same device is required, like if your system is like the environment, like if you interchange system and environment, if you're required to take heat from the absorb heat from the environment and dump it in your system, then it becomes a heat pump. Okay, and Clausius statement talks about the feasibility of a refrigerator or slash a heat pump. See, what is a heat engine doing? Let's just quickly see this. It is giving, it's absorbing some heat. Okay, it is absorbing some heat. Let's say Q. I'll put power rather than putting heat. I'll put power, thermal power, and then it gives you work. So mechanical power, right? And in that process, it has to. The second law says that you also have to reject some amount of heat. So for that, I'll try to say what that I'll use this file just to distinguish what is like necessary and what is uh, like can't deal with it. It is a necessary evil, right? So Q eject. Okay. And this is Q inject. Now, if you think about it, if you reverse this process, see, you can't reverse this process, right? You have to, if like refrigerator does the exact opposite thing. What does it do? It takes heat and it also takes work. Okay, to pump and heat into the surrounding, or what do I mean by surrounding? Into a high temperature source, high temperature reservoir. Okay, let me clearly say. So this is how refrigerator is defined. See, the border, the thick arrows mean this is what it is expected to do. See, efficiency of a heat engine is W by Q injection, isn't it?
Yes.
Right.
Yes.
For a refrigerant, what is it? It is see for the performance of these devices are connected by these orange arrows. Okay, so in this case, what is the thing? Thing is, this is your injection, and then you reject. Okay, and here your coefficient of performance will be uh, how much heat have you rejected? Q injection by W dot. I think this is how coefficient of injection performance is defined. Let's see. For a
So,
for a reference. Huh.
so basically, what is the desired effect that we have to see? So, in case of the refrigerator, it should be the uh, Q taken from the lower temperature source upon the work input.
Yes. Can
And
I just pause and take like just 2 minutes? I'll just take 2 minutes. I'll pause. Okay. I'll
okay,
unmute myself.
please.
Yeah. Hello.
Yes.
Can you so basically you were reiterating what I was trying to explain, right?
Yes. Yes.
You were like confirming that we have to take the effects, the contributions that the effects that we want, right?
Yes.
For establishment of performance.
Yes.
Yeah, you
So
go ahead.
basically, in case of heat engine, what happens is the work generated is positive from the system, but in
Yes.
case of heat pump and refrigerator, it's always the negative work involved. Now, next is what is our target? So in case of the refrigerator, it's basically about the Q that is being taken out from the lower temperature source. That is QL,
Yes.
and upon the work
Hmm.
input. However, the heat pump, it can be the same thing, but the desired effect is that how much heat load is being transferred at the higher temperature end. That means QH upon the work input.
Exactly what that is what I was trying to also communicate. Exactly. So that is exactly what I wanted to say. And this is, if you note, this is the COP. This is how they define the COP for these two. Okay, and this is not explicitly told, so this can sometimes become confusing also. I just told you so that it becomes apparent to both of us, like to everyone who is watching these lectures. So just look at how in a heat pump, as you have already understood, this becomes not injection but Q dumped, or Q rejection also I can say, Q rejected into the atmosphere. And in this one, this becomes, so the reason I'm saying injection and rejection, uh, I'm talking in reference to the device. If the device is there is a heat addition to the system, then it is called Q injection, and if it is getting rejected, then I'm calling it rejected. If you're removing heat, irrespective of what temperature the surrounding is at. Okay, so it is not associated with the surrounding, but it is associated with the direction of heat from the device. Okay. Okay. Generally they call it QH and QL, but I don't want it to do it. We can call it QH and QL also. Then this becomes uniform across the three devices. But I didn't want to do it. I just wanted to emphasize that what are the important effects, just like exactly what how you have understood. So the point is that a refrigerator actually operates as a heat pump and not as a heat engine. So I think that corrects this statement also, right? So there should be
Yes.
heat. Think I don't know anything else. There is no need of any other further clarification. Anyways, so yeah, let's move on. Okay. The fourth
Oh,
question. Yeah, pick the correct option. It says so. Again, we have to. This is again. Okay, let's do this. Simple only. All reversible processes are quasi-equilibrium processes. All quasi-equilibrium processes are reversible processes. Both of the options are correct. Both options are wrong. These are the four options we have. Okay. Rather than Jyotirmay ji, please answer it if you would like
I
to.
think it should be option A, because all reversible processes should be quasi-static, but all quasi-static processes need not be reversible in nature.
Let me think. Okay. Okay. Hmm. Can you explain further? Like in three sentences, can you tell me why you chose this one?
Because for a rever- because from the thermodynamics point of view, a reversible process is something which we should be able to fully plot on a graph. Let's say from point A to point B. If it is undergoing a system, it is undergoing a process. Now, within that line, we can only plot one point when we assume that the system, in that particular system, it's throughout the continuum, it is in equilibrium. It is in the same state. So for that, it is should be quasi-equilibrium. But however, even if it is a quasi-equilibrium process, it not be reversible in nature, because if there are some friction losses, etc.
So our friction losses does a friction loss not make a system non-quasi equilibrium? Mm, okay. There might be some processes, some dissipation that happens in quasi-equilibrium processes. Let me think. So this is the correct answer, by the way. This is you chose A, right?
Yes, yes.
The
And your
correct option.
question was
Hmm.
that do frictional effects are also quasi-equilibrium? So
No, do they like if there is a friction, can we call the process quasi-equilibrium?
I mean, mm, I don't know. Maybe I think it should not be. But is there any explanation for that?
Let me check. Although this option is correct, but I still have reservations with this option. Let me see. At least, okay, let me see. Okay, so this is what it says. Yeah, this is correct. Basically, this is saying if there is any uh but okay. So I think this table will make sense. Let me, so whatever, what was I doing all this while? Let me tell you. See, in ChatGPT is very best for these type of discussions because it has all that knowledge on internet with him. So the first question I asked was, can we have an irreversible quasi-equilibrium process? See, this is the whole point, right? My confusion was that, see, my general understanding of what a reversible process or irreversible process is. Let me try to first propose that. See, the way I understand reversible processes is that if there is any type of, so irreversibility comes from non-equilibrium. Let me tell you that. This is a well-established fact. Okay, I'll tell you why. Assume, do you agree with me?
Yes, yes, I agree. Please go ahead.
Yeah, you agree, right? So any irreversibility should come with non-equilibriums. Now, in our in our pursuit to say call it quasi-equilibrium, we are essentially saying that the non-equilibriumness is infinitesimally small, right? It is negligible, which makes it reversible, right? Which makes this process reversible, isn't it? So
Yes.
any quasi-equilibrium process should be a reversible process as well. If you have a quasi-equilibrium process, there cannot be any what do you say, any non-equilibriums, and then you should have the processes what do you say, reversible. So this was the issue. So I asked him explicitly, can we have any irreversible non-equilibrium process? So like you said, it said that if there are some dissipative forces like friction, viscosity, finite temperature difference, then this becomes a this becomes a irreversible process. But my whole point was that friction, viscosity, finite temperature difference are non-equilibrium effects. Okay, do you understand? See,
Yes.
when
Yes.
you have
Yes.
finite temperature difference, that means that you are in a non-equilibrium with the surrounding. If you have friction, that means that there is a velocity gradient between you and your surrounding. So I asked it. See, I asked, but does friction not imply non-equilibrium? So it says, great question. This touches a subtle point in thermodynamics. Friction is fundamentally a non-equilibrium phenomenon. True. It occurs because there is a velocity gradient, there are shear stresses, uh, and these require departure from thermodynamic equilibrium. If a system were in true equilibrium, there would be no motion, no gradients, no dissipation. So the subtle point is it in a true equilibrium or is it in a quasi-equilibrium thing? In a quasi-equilibrium, it is arguing that although the non-equilibrium thing is infinite symbol, but it is still not exact, right? There can be infinite symbol irreversibility. So there can be processes where infinite irreversibility can accumulate over time to give you irreversible processes, because quasi-equilibrium does not mean true equilibrium. So yeah, I think this is pretty obvious also, but got confused, so I just asked ChatGPT. I think this is fine. So you understand, right? Quasi-equilibrium does not mean that it will be true equilibrium. Okay, so maybe I'll write that here. The key takeaway is quasi-equilibrium, not true equilibrium. I felt this is quite important. Anyways, because I think I would get confused again, because for me quasi equilibrium is equilibrium, but this is important. It is not true equilibrium. There can be small irreversibilities, and over long periods of time they get accumulated, so you cannot come back. That's the logic. Okay, fine. Then let's go to this another question. See, the problem, I'll tell you what the problem, the issue I have is there is no quasi equilibrium processes also. Just like how there is no true equilibrium processes, quasi equilibrium processes are as far fetched as a true equilibrium process. A true quasi equilibrium process will make it reversible. Anything reversible. If you are, say, friction is important, then you can't call it quasi equilibrium, right? You will say that slow further down, right? So that it does not if you're like quasi equilibrium means that you are always at equilibrium. So again, it's kind of a fine line. Uh,
So while interpreting these lines, and can I say that the quasi-equilibrium word and the quasi-static word, it has been used interchangeably?
yeah. So quasi
Okay.
equilibrium and quasi static are used interchangeably. Yes, that's true. There's a fine difference also. Let me tell you a small difference. There is a small difference. Not that it is very important, but still, let me point that out. What is the literal meaning of quasi-static and what is the literal meaning of quasi-equilibrium? Quasi-static means that the process, quasi-static means the process, there is no unsteadiness. Let me again chat GPT it. Test.
Okay.
Ah, because there is a there we again somebody might argue that they are different. So let's have the differentiate between quasi-static and quasi-equilibrium. So many of them use interchangeably. It points that out. A process that occurs infinitely slowly. That's what I thought. And infinitely similarly close to thermodynamic. Okay. Uh, Slow but can still be irreversible. If no dissipative exists, then it becomes reversible. Okay. See, the difference is quasi-static means that there is no unsteadiness. Now, what do you mean by unsteadiness? See, see, time or unsteadiness is also a irreversibility, right? Let me ask this, if this is a correct statement, that unsteadiness in itself is a irreversibility. Let me ask, is it correct? So basically, what I'm trying to postulate or trying to say here is that unsteadiness also brings irreversibility of its own, non-equilibriumness on of its own. Because see, this is what is a true equilibrium. True equilibrium. There are two types of equilibrium, right? One is the system is becomes homogeneous. System is in equilibrium with itself. So wherever you go, it becomes uniform. Wherever you go, it's the same properties. And another equilibrium is with the surrounding. There are two equilibriums, to be honest. And generally, people don't talk about these two things. Uh, for true equilibrium, see, a true equilibrium will mean that your system is in equilibrium with the surrounding, right? A quasi equilibrium will imply that that your system in its own is not varying so much that there is a spatial inhomogeneity. The uniformity breaks. There is a non-uniformity. Okay, so these are like closely. So this is what I'm trying to say. Let me ask this question to ChatGPT. Is it correct to say that unsteadiness, non-quasi staticity brings or is an irreversibility, brings irreversibilities of its own. So what do I mean to say is that see, there are primarily three irreversibilities. There's the mechanical irreversibility, there's a thermal irreversibility, and there is another in simply compressible systems. Mind that in the systems that we generally talk about, thermodynamic systems, there can be only three irreversibilities. Mechanical, where there's the pressure variation across the system and the surrounding or inside your entire system. If the pressure varies, then definitely there's a pressure gradient, and then that will result to flow, or that will result to some movement of the boundary, and that will cause you to have non-irreversibility, right? Then there is a thermal irreversibility, which will cause you to have heat transfer, right? And then there is another reverse chemical non-equilibrium where these species move. And you know what? I'll tell you this. Nobody talks about this enough. Every irreversibility becomes a chapter in mechanical engineering. So pressure irreversibility becomes fluid mechanics. Temperature in equilibrium becomes heat transfer, and chemical in equilibrium becomes mass transfer. That is why thermodynamics is taught as separate, and like is taught separately from these two other topics. When you have pressure differences, then flow happens. Then viscosity also would pitch in and all those things. Because viscosity happens, then there is a viscosity is basically that your velocity, there is a gradient and velocity differences are there, right? So all those things are there. So anyways, let me ask, if does unsteadiness also brings its own irreversibilities? What do I mean by that? That out of like, will unsteadiness also cause mechanical irreversibility, thermal irreversibility, and chemical irreversibility? Because I'll tell you, any system you have, any realistic system you will have has a relaxation time. Any system, if you subject it to changing conditions fast enough, then it will not be able to react to those changing conditions. See, suppose, what do I mean? What do I mean is that generally in all engineering specific problems, that relaxation time is very close to zero, and so it does not matter to us. So we can kind of assume that our system uh, reacts to this reacts to surroundings or whatever immediately. But if there is unsteadiness, then actually this is called non-equilibrium thermodynamics, to be honest. Okay. Whatever I'm getting into is a little advanced in that sense. I'll show it to you. What do I mean? Non-equilibrium thermodynamics is when this unsteadiness picture comes in. So let me tell you that. Let me
Sorry to
search this
interrupt.
for you.
Sorry to interrupt. I can. Okay, I'm seeing your screen now. Okay.
Okay, okay. But do you are you getting what I'm trying to hint? Like, you're able to understand, right?
Yes,
Whatever
yes,
I'm trying to.
basically, like how the gradient existence of gradients is trying to drive some, you can say, reversibility, different type of, like
Yeah,
unsteadiness,
yeah.
for example.
Yeah, actually, if you have this unsteadiness is very fast, then you will have non-equilibrium thermodynamics. And non-equilibrium thermodynamics means that your system will not, like, thermodynamics is all when you have quasi-static conditions. Sometimes this also fails. Okay, so that deals with physical systems that are not in thermodynamic equilibrium but can be described in terms of macroscopic quantities that present a. Okay, let me ask this. Uh, and is this somehow related to non-equilibrium thermodynamics? You know how it is so funny, because we say thermodynamics, right? But actually we are learning only thermostatics. We are not learning thermodynamics. Dynamics means unsteady conditions and variation with time and so on. Actually, we are learning only thermostatics. It's called thermodynamics, but we are always dealing with quasi-static conditions, slow processes and so on, right? So it's not dynamics precisely, but anyways, largely correct, but it needs careful qualification to be thermodynamically precise. Does unsteadiness introduce irreversibility? Often, yes. If a process is not quasi-static, it proceeds with finite driving forces such as finite pressure difference, finite temperature difference, finite velocity gradients. All of these generate entropy, rapid expansion of a gas, pressure inside is not uniform. So non-quasi-static processes typically create irreversibility through gradients. That is what I wanted to say. So your system will start to have non-equilibrium in itself, non-uniformity. So gradients will start to form. Whereas when I generally talk about quasi-equilibrium, I'm basically talking about my surrounding and system. I'm comparing that. Now, quasi-static will mean that it is slow enough that your entire system remains homogeneous. It does not vary. But unsteadiness itself is not a fundamental cause. So if your system is very slow, but it is still unsteady, then your entirety of thermodynamics and your theory of thermodynamics still holds. This is what it will say. You can have unsteady but reversible motions in mechanics. In thermodynamics, however, fast processes almost always create gradients which lead to dissipation. That is why we say slow processes, so that there is no gradients that form. Connection. And yes, this is exactly the domain of non classical thermodynamics assume equilibrium states or quasi-equilibrium processes. When processes are not quasi-static, the system may have spatial temperature gradient, velocity gradients, chemical potential gradients. Non-equilibrium thermodynamics studies relations like flux, which is function of thermodynamic forces. Let's leave these things. Um, so, anyways, again, our entirety of the discussion does not lead us to anywhere. But essentially, I would just wanted to point out that there are two types of equilibrium that we generally talk about. One is the homogeneity of your system. If your system is, if your process is not slow enough, there will be internal gradients there. That is one thing. And then the quasi-equilibrium generally means uh, equilibrium with your surrounding. Okay, so they are kind of used interchangeably though. That is the that is the big picture. That is the big statement. But again, there can be integrities. At least that is what we can say. Anyways, okay. So I think this is fine. We discussed too much and went no. Anyways, but this is a little complicated there. That is what I wanted to say. And mind that there are no universal definitions around it. Okay, no textbook talks about in great detail. Might be there might be good discussions in some theoretical very high standard literatures, but at least in textbooks level these things are not there, at least in UG textbooks or anything. Okay, so because generally we look at the simplest case. So in simplest case, everything's fall down to the same thing. Quasi-static, quasi-equilibrium means the same thing. So all does not really matter to us then. So, okay. So you can largely use them interchangeably. So now let's get to this question. Somebody claims to have developed a new reversible heat engine cycle that operates between temperature limits same as that of Carnot cycle. Which of the following is correct? Thermal efficiency of device 1 is greater, device 2 is greater, and the well, we know that we know that this has to be option B, right?
B, yes, option B, yes.
Yeah. Option B. Now let's move on
Option B, yes.
to another question we have. Fuel is completely burned first with the stoichiometric amount of air, then with stoichiometric amount of pure oxygen, for which case will the adiabatic flame temperature be higher? Don't know why these questions are merged here. These guys have mixed it up. Let's do it towards the end. You'll see what flame temperature is and so on. Towards the end, we'll see. Okay.
Okay.
Food department. Okay. By any chance, did sir teach all this in this week's course, this week's lecture, or is it like a mess up on the NPTEL side?
No, actually, this was covered in this week's lecture.
Adiabatic flame temperature and all.
Mhm.
Okay, so that means that they have not messed up. This Hess laws and all that has also been covered. I
Yes.
feel Hess law has been covered, is it?
The reaction, yes, there was a chapter on these reactions in which it was covered, I think. The Hess law exactly, I don't know, but the chapter on the chemical reactions has been covered.
Oh, which lecture number would you mind to tell me? Which lecture number?
I think it is lecture. I think lecture number 19.
19.
Oh,
Okay,
yes,
first, okay. Reacting systems. Okay.
lecture 19.
Yeah, even I see this now. There is this lecture out there. Okay, let me copy this then. First law application to chemically reacting systems. Okay, fine. We'll do it towards the end then. Food department is kept at minus 12 degrees Celsius by a refrigerator in the environment of 30 degrees Celsius. The total heat gain to the food department is estimated to be this much. Uh, Heat rejection is this much. Determine the power output of the compressor and the COP of the refrigerator. We can do it, right? First law and then the definition of efficiency we have used.
Yes.
Okay. So, okay. So what is it? So I'll use this formula. This for the see this whatever I'm going to write now will be valid for all three of them: heat engine, heat rejection, sorry, heat engine, refrigerator. And okay, you check it out. This always holds. There. So then, okay. So now we know what is QH. QH, the total heat gain to the food department. Uh, so we know that QH is 4800. Then QL should be 3300. And in this equation, no, in this equation, all three of them have to be positive. Mind that. They cannot be negative in this. If they are negative, then sign changes. In this, all three of them will be positive. So in this one, I know W dot is what? W dot is 1500. Uh, Determine the power input to the compressor. Okay, so I think power input to the compressor is 155 kilowatts per, this is kilowatts divide by 3600, isn't it? So this 00 goes away, 15 by 36. Is it like what, 0.41 or what? Yeah, so it's 0.417 kilowatts. Okay, this is this one. And we no more want to, like, no more need to calculate COP. But anyways, let's calculate COP also. So COP will be, as I told you, this is a refrigerator. So the effect we want is QL divided by W. The effort we are, like, the effect we are giving is QL. The effort that we are effect that we want is QL. Effort that we are giving is W. So 3300 divided by 1500. And this is 2.2. Okay, so this matches. Make sense? Is that okay, Jyotirmaji? I didn't do it properly. I just did it hand wavily, but we are quickly we can get answers. Is it okay? Do you want me to do it
Sorry,
properly?
sorry. I think yeah, B is matching.
Okay. An automobile engine consumes this much fuel at a rate of this, delivers this much of kilowatts, so it's giving power. If the fuel has a heating value of this much and a density of this much, determine the efficiency of the engine. Again, power is known and Qn is known, so we just need to substitute the values and see if this is what we need to do, right? Let's see. So what do we need to do? Let's quickly see. So we know the volume flow rate. So we can quickly multiply and see, find out the mass flow rate, right? Mass flow rate we can quickly find out. And then we have specific heat capacity. No, this is, yeah. This is not specific heat capacity. This is a what? This is specific heat capacity only. No, this is specific heat, not specific heat capacity. This is specific heat. Okay. Do you know the difference between specific heat and specific heat capacity? Cp is dH by dt. But specific heat, I don't know how to write specific heat as, but specific heat is generally H by H, H by M. So it has units of kilojoule per kg. So this is specific heat is given. So efficiency will be 60 kilowatts into times 1000, and then this will be 25 liters. So 1 liter has 1000 meter cube per hour. So you also need to multiply 3600. Then you have 0.8 gram. So times, so 0.8 gram becomes zero point 0.8 by 1000. Centimeter cube becomes 10 to the power 6, right? So 2000, these thousand goes away, okay? This thousand and thousand will go away. This is one, and this will also go. And then I also need to multiply 50,000 times 50,000. And see, this is also kilojoules, so I can remove this kilo. This becomes 60 kilowatts divided by 60 kilojoules per kg, and this is kg per second. So this is dimensionally fine. I can go ahead and cancel these two zeros also with these two zeros and another one here. So this is just 50. And do you know what 8 times 50 is? 200, right? 8 times 25 is 200.
Times 20, 200, yes. 825.
Then 50 is again, this zero can be gone. Like this becomes another, there was one additional zero, and then this becomes 10, right? Uh, yeah, and then 1 0 I can take away from here. So this becomes 216 because 36 gets multiplied by 60. So 216 divided by 1000. So this becomes 0.216. This should be 22%. Is that okay?
Yes, it seems okay. 22% around.
A household. Okay, let's go ahead and do this one also. Okay. So a household refrigerator has this much power input. COP is this 10 kg each. Okay, are initially at 25 degrees Celsius. How long will it take for the refrigerator to cool those watermelons? The watermelons can be treated as water whose heat capacity is this much. Okay, so we know COP, right? It has W is what? Power is, oh, wait, yeah, power is 500 watts, right? We have COP of 2.5. So can you tell me, Jyotirmay Ji,
Yes, sir.
Will be our QL, Q dot L. By just by just remembering the fact that for a refrigerator, COP should be equal to by effect divided by effort. Effect is QH, no QL, and effort is W.
Yes. So Q, okay.
Jyotirmaji, did you find what is Q dot L?
Okay. So over the QL should be equal to, there are 5 watermelons, okay, into 10 is the kg of MCP, and then is the 4.2 into this 4200 4200 by T, okay. QL is 20. So the T comes out to be around 1260.
1260.
No. Sorry, it should be 5 into 10 into 15 into 4.2. 2500. So it should be equal to 1.26. 1.26 it's coming.
1.26 seconds.
It is kilojoule per second. 4.2 kilojoule. It's there. Actually, the power input we have is in the range of 500 watt, not kilowatt.
Okay. Yes, you're right. Then it becomes a 4.24200 then, right?
Yes. That is 1260 and 1260 seconds, and this divided by uh,
Hey, I've done this incorrectly or what? This one is wrong. No, wait. 25 fives are 125, 1250.
QL is 1250. QL is because it is basically COP into WN. Yes.
Yeah.
1250 watt. Yes. Now this 1250 is the Q from the lower surface QL. Yes. And that should be equal to 5 watermelons into 10 kg each. And the watermelon, 10 kg each into 10 degrees Celsius. So delta T is 25 minus 10 into CP is 4.2 kilo.
I'll just take a break and I'll just come, okay?
Okay.
So if you solve this, T is actually coming out to be 4. Actually, it can be seen from here also, is it? Let me see. See, T has to be, if you have to divide it, you have to put it in minutes also, no? So if I multiply by 60 here,
Hmm.
because
So
I'm
from here,
saying
actually,
whatever I'm on.
so while solving, we get T is equal to 2520 seconds. And that if you divide by 60, then it is coming to be 42 minutes.
Yeah, I think it can be seen from here also. Let me try. 420 gets cancelled here. Will come, right? It should come. Forty-two minutes, as you said.
So that is the right answer?
Yeah, that is the right answer.
Okay.
Okay, so this one is the right answer. Okay, so now let's do the next question also.
Oh, Shreji, maybe can we please take up the chemical reaction questions first? Because
Okay, so you want to do the chemical reaction questions.
yes, actually I have to cover that. So
Okay, so those ones. Adiabatic one, first of all.
it is this one actually.
So as you mentioned, Hess law is actually addition of all the total enthalpy of change of reaction depends on the reaction pathway. It does not. So that's totally incorrect. The total enthalpy change of a reaction is independent of pathway and depends only on the initial and final states. That seems to be true. The enthalpy of change of a reaction is always negative. It does not say anything of that sort. And it depends, right? It can be exothermic or endothermic. So this is also wrong. The enthalpy change of a reaction depends only on the number of reactants, not their physical state. That should be definitely incorrect. I think this is the correct answer. And then this question, a fuel is completely burnt first with stoichiometric amount of air and then with stoichiometric amount of pure oxygen. For which case will the adiabatic flame temperature be higher? Okay, so let me open this up. Let me see. I don't remember adiabatic flame temperature is. Okay, would you like to solve this one or explain why? What do you think?
Actually, I require your guidance a bit on this.
Okay. Okay, you want me to solve it?
Yes, I will follow and then I will understand.
Wait, let me open up the section on adiabatic flame temperature and then we can try to solve this. You understood the Hess law one, right?
Yes, yes, that is for the enthalpy associated with chemical reaction.
Exactly. The air has less number of oxygen molecules. Okay. Stoichiometric amount of air. So whatever fuel is required. Okay, no, wait. They might have the same temperature, isn't it? Stoichiometric amount means complete combustion. Let me see. Oh no, let me see. Okay. See, the answer is 2 only. Okay, and I'll try to explain it. It's pretty simple only, not something big. See, stoichiometric amount means that you say whatever the fuel is, and it requires this much amount of oxygen. Then stoichiometric amount would mean that this much, if you have 1 mole of fuel, then X amount of oxygen should be there. X number of moles, X number of oxygen moles should be there. Adiabatic fuel temperature means that whatever the enthalpy of your chemical reaction is used to heat the products, the mixture of products. Now, and there should not be any heat losses. So in case there is no all kind of enthalpy goes into heating it. No, so that is why it's called adiabatic. So there is no heat loss. Okay. Now the the question the catch here is that the number of oxygen moles in both cases will be same. So the reaction and the amount of enthalpy generation will still remain same. But with air, you will have an additional amount of nitrogen, right? So you know air is 70% nitrogen, 20% oxygen, roughly 20%, 18% oxygen, and 2% whatever else there is, right? Uh, I think even not even 18%. It's what is the composition of air? Let me check. It's 19.9%, I think. 19.78%. Sorry, so I made a mistake. 78% is nitrogen, 20.9% is oxygen, and only 0.1% is rest of the molecules. So then, because nitrogen, your end products uh, will have more like will have large number of nitrogen moles. So that will that will have an additional heat capacity, right? So you have a more thermal mass in your product compared to when you have pure oxygen. So your adiabatic temperature will be higher when you have only pure oxygen. In case of pure like air, it will be lower. It's if you think about it, it's called a rich fuel mixture and lean fuel mixture kind of stuff. So this is a very rich. No, this is no, that is different. That is in terms of fuels. So no, that whatever I said about lean and rich, forget about it. The adiabatic temperature in this case will be higher for pure oxygen. That's the bottom line. So yeah, I think there are more questions on. Uh, this reaction part only. So let's do this. We take it to a different slide. Determine the standard heat of reaction for the famous water gas shift reaction. Following informations are given. So we want to find the enthalpy heat of reaction for this reaction, and then enthalpy of formation at 25% degree Celsius and 1 atmosphere is this much for CO2. Should be all one files. Okay. So this is for CO2, for H2O, and for CO it is given enthalpy of formation. Now, would you like to try to solve this? Let me quickly check. This part I have not prepared, so I will have to go back to the textbook and see. Enthalpy of formation is what? Okay, right. For carbon dioxide is this. Okay. So, given Jyotirmay ji, given that you have undertaken the lectures, video lectures, I'm seeing that this question is also straightforward. Would you like to attempt it? It's not very difficult.
So
I just had to look up the definitions of enthalpy of formation and other things to solve it.
it will be good if you please guide me for this question. The next ones I can maybe take.
Okay. So the idea here is, it's basically the Hess law we discussed, right?
Yes.
So it's
Yes.
basically in an attempt to find the enthalpy of enthalpy heat of reaction, uh, what we need to do is subtract heat of for enthalpy of formation of the products from the enthalpy of formation of the uh, so we have to subtract enthalpy of formation for the reactants from the enthalpy of formation for the products. That's it. That is what we need to do. Okay, because Hess law says that, right? Hess law says that your heat of reaction or enthalpy change of a reaction is depends on your initial and final states. And final states at ambient conditions and whatever like these normal conditions will depend on enthalpy of formations. Now, enthalpy of formation, what do you mean? Enthalpy of formation means enthalpy of reaction from coming from its stable compound. So basically what we need to do is add all these components. So add the enthalpy of formation of the products and minus the reactants. Mind that enthalpy of formulation of hydrogen will be zero because it is already a stable compound. It is not getting formed from any other. It's a molecule, right? It's a pure molecule. It's not getting formed. It's a stable ingredient. There will be no reaction that is going to happen. You understand?
Yes. But then if you look, then even carbon dioxide is stable. CO2, if you see over here.
Yeah. But it is a compound. It gets formed from stable carbon and stable oxygen.
Okay. But this is
But
elemental form. Okay.
yeah, it's an element, right? So we this for this or let me feed this question to GPT also and see how does it try to solve it. So you just have to add it. There's nothing much to be done there. I'll just feed this to ChatGPT and see how it tries to solve it. If does it give a different definition explanation for H2? Let me just see. So as I said, products minus reactants. Uh, so so for H2, element is in standard state. So that is why it's zero, and then it solves it, and the answer will come out to be what? Can you tell me now? The key thing is products minus reactants.
Yes, and we have to multiply it also by the moles. So over here,
Yes.
all of them are in one mole only. So if the H2 is
Yes.
zero, so we have CO2. So for CO2, it is minus 393.51. Minus 393.51 kilojoule per mole. And for CO2, CO is 1110.5 times. Should it be option B?
Oh, how did you get that?
Well, first of all, we write the reaction as it is, like CO2 plus H2 is equal to this. Now, if we look into the left value, so it will be 1 into the means the enthalpy formation for CO2. So that is minus 393.51. And let's
So
just keep it
minus
like
of
that.
minus that. Note that minus of minus that. See, this value is minus in itself. It's a negative value in itself, but you have to subtract that value from the products. You understand?
Reactants. Oh, okay, yes, right. Okay, so it will be. So the enthalpy of standard heat of reaction is enthalpy of formation of reactants minus products, or is it like products minus reactants?
Products minus reactants.
Okay, products minus reactants. Then it will be. So it's coming then plus 262. It's coming.
No, you have done it incorrectly.
Well, I'm a bit.
How have you done it? Tell me. How have you done it? Oh, you tell me. I'll write. You tell me how to solve it. Okay. You tell me.
Okay.
I will write on behalf of you. You tell me how to solve it. You tell me the numerics. How will I get the answer?
So
What should I add and what should I subtract?
Okay, so I will write it like this. Starting from CO, so I will say 1 into 1110.59.
Right.
1 into 1110.59.
Right.
59 plus.
So there's a
into,
minus. Okay. There's a.
No, it should be
there's-
plus because we have product side plus.
No, but there's a minus in itself.
Achha,
The value is negative.
Okay. So it will be then minus. Sorry, minus 1110. In brackets we can keep. Then.
Yes. Actually, this question, the way I've pasted it, it was not clear also. So anyways,
Then plus.
Then you tell me.
Plus it will be again 1 into for H2O it is minus 241.82.
And then
This should be the reactants minus 1 into for CO2 it is given to be minus 393.51.
Now tell me what will the answer come?
It is minus 11. Okay, so it will be like minus 1110.59 minus 241 minus 241.82 minus. Yes. So now it's coming to be 41.1 plus.
Yeah. That is the correct one.
Okay. 41.1 kilojoule per mole. Okay. Okay, this sign I made a mistake. Sorry.
Yeah. I think this is okay. Yeah. You have any questions?
Well, actually, this part I have not fully covered yet towards the last, but otherwise, I don't have any questions.
Yeah, you can come back. We can discuss this next time also. So
Sure,
at this point, I'll close. Now, and we'll.
Sure.
Yeah.
Thank you for your time and the guidance.
Yeah. Thank you so much for attending, and see you next time. Bye.
Thank you, Shreji. Bye.
Thank you, Jyotirmaji. Bye.
Bye.